Hello teacher, our group 7 today we talk about our mini project of forecasting and tuning class. Our community name is Pharmacies and Drugstore. Move first, the task one is display and collect data ET. As A, you can see here we have the clean and reprocess the time series. And here, moving next to the B, we will analyze the received static for all data series ET. First, I will give a brief comment on this data. You can see here the sample size n equal to 403. It's after we have data processing in A, so we have large enough to ensure the reliabilities here. Uh, the two value including mean and median is same at the 17. So you can understand that the central the tendency is equilibrium balance. The standard deviation equal to 7,000. So the coefficient variable here is nearly 43%. So the data with the high volatilities in dispersion. Okay, as the also has the histogram of ET value. The data columns in do not fit the bell curve perfectly. You can see here. It also have a multi-peak and spread out chart. So the data is distributed sporadically and do not closely follow the normal distribution curve. Move next into we have the probabilities plot of ET value. So you can see here the AD or Anderson-Darling static value is equal to 3.082, and also the p value is less than 0.005. So you can understand that the data does not follow the normal distribution, and the CV at 43% you can calculate before. So the data is not tightly clustered around the mean, but it's spread out. You can see here it's spread out. Okay, and the final the street. You can we have the goodness of fit test. The p-value less than 0.05. There's no distribution meet the criteria. The well-born distribution have the lowest error with an error of minus 2.667. So we choose the well-born distribution as the model that's best to sweep the data we use.
Task 2. Characterization of time series. Question A. Firstly, about train. We draw four train models and find that the train is upward and one traffic is the best fit, which has lowest MAD, MSD. Secondly, we draw AFC of last 5 years and identify that the time series has the seasonality repeat year after year. For example, at leg 12 and 24 in the diagram. And then we find that there are many outliers, especially at the end of the time series. And about long-run cycle, we see that the cycle component fluctuate up and down the trend level. And time series has inconstant variance. It has small fluctuation early, but larger fluctuation later, and there is no eruption in data. Here is a free-order trend model. Question B and C, we choose one static trend because it's a best fit trend model, and the limitation of the model is that it doesn't have seasonal component. And we choose decomposition additive because it can capture trend in seasonality, and additive model because seasonal fluctuation have roughly constant size over time. However, the trend component is a particular function, and seasonal indices is unchanged over time. And we choose whole winter additive because it can capture trend and seasonality with update of the recent data. So it's a better real-time forecasting. But if smoothing constant is very small, it leads to the data is smoothly, and it may react slowly and otherwise. So we identify the best method is whole winter, and we choose two methods, decomposition and whole winter, to forecast. About whole winter, the error matrix MAPE equal 2%, very high accuracy, MAD equal 364, MSD equal approximately 270,000. These values are low compared to the value of the data, and the fitted line follows the actual values almost perfectly. And about forecast, these forecasts are smooth and follow the actual trend and seasonality. This is the most accurate and most suitable model for this time series. About the composition model, it has higher error. MAPE equal 5%, MAD equal 806, MSD equal approximately 1.3 million, 5 times bigger than winter method. This because the decomposition method assumes seasonal indices do not change over time, and trend component is follow a linear trend. Here we can see, and but the dataset has a curved trend and strong growth toward the end, so the decomposition cannot capture this increase. And about forecast, the forecast fails to keep up with the strong lay series growth, so it's under forecasting. And here are the free period forecast in whole winter model. It's possible to identify the confidence interval.
Now let's move to task 3, perform forecasting by applying multi-variable linear regressions. And this is part A, how I select 5 independent variables x1t, x2t, x3t, x4t, and x5t. So first, I select 5 core predictions that capture both demand and supply side dynamic. For X1T, I choose employment in health and personal care retailing, reflects the scale of the pharmaceutical retail market. For X2T, I select average weekly earning in good producing industrial, represent household purchasing power. For X3T, I select industrial production of consumer goods is a proxy for the availability for non-durable items, including OTC health products. And next, for X40, I select employment in wholesaler trade reflect distribution capacity and the efficiency of the supply chain. And finally, I select X5T is the consumer price index is converted to good warning bad category to represent low, medium, and high inflation regimes. Together, this variable provide a structured economy view of how market size, income, production, distribution, and inflation jointly drive pharmacy sales. Now let's move to part B. Generate the missing data for XXT and convert the CPI index into the categorical variable. In addition, we create a variable x6 from a uniform 0 to 10 distribution in Excel. This serves as a purely random benchmark to test whether predictions appear significant. And next, for CPI, we use the 33 and 66 percentiles of its distribution to build 3 categories. Value below 33 percentiles are good, indicate low inflation and a supportive consumption environment. Value between 33 and 66 percentiles are warning, where the price pressure starts to appear. Value below 66 percentiles are bad, reflecting high inflation and quicker real purchasing power. These formations keep the tree-level structure but make the category balanced and economically interpretable for the actual CPI data. Now let's move to the final part of task 3. Part C, perform a regression, analyze results and test hypotheses, and then propose solutions to address any violations of model assumption. First, overall model fit and global hypothesis testing. The regression model achieved an R-square of 98.55% and an adjusted R-square of 98.53%, meaning the 6 predictors collectively explain almost all variation in pharmacy and drugstore sales. The ANOVA F-test gives an F statistic of 4,479.64 with a p-value below 0.001. We test the null hypothesis that all slope coefficients are equal to 0 versus the alternative that at least one coefficient is non-zero. Because the p-value is extremely small, so we reject the null and conclude that the model as a whole is highly statistically significant. Second, individual coefficient test. Most predictors are statistically significant at conventional level. Employment in health, retail, earnings, industrial, production, and CPI category all have positive and highly significant coefficient. Indicates that larger markets, higher income, stronger production, and favorable or structured inflation regimes are associated with higher sales. The coefficient on wholesale employment is significant but negative, which may capture structural effects or cost and efficiency pressure in the distribution system. By contrast, the auxiliary variable x6 has a p-value around 0.25, so it is not statistically significant and behaves exactly as a random noise factor, which confirms the robustness of our economic variable selection. Third, multi-collinearity diagnostic using VIF. The variant inflection factors so that x1, x2, and x5 have VIF values around 8 to 10, indicate high to very high multi-collinearity. x3 and x4 have moderate VIF value and x6 have a VIF of 1, meaning no multi-collinearity. High multicollinearity inflect standard error, make coefficient estimate unstable, and make it difficult to interpret the individual impact of correlative prediction. In other words, while the model fits extremely well, some of the coefficients are not numerically comfortable due to overlapping information among the predictors. Fourth, outlier and influential observations. Several data points show that standardized residual larger than 2 and relatively high leverage or Cook distance value. These observations are not extremely extreme, but they do exert noticeable influence on the regression line and on the estimate coefficient. If they are left unchecked, they may distort both interpretation and forecasting performance. Fifth, assessment of key regression assumption. Linearity appears to be properly satisfied given a strong and significant relationship. Independence of residual is slightly violated because we are working with monthly time series data where autocorrelation is common. Multicollinearity is clearly violated, as indicated by the VIF result. These issues do not destroy the model, but they signal that more advanced time series regression framework is needed to reliable forecasting. And the final, recommendations for model refinement. To improve statistical stability and forecasting accuracy, we recommended remove X6 since it is not significant and only adds noise. Reducing multicollinearity, for example, by using stepwise regression, principal component analysis, or dropping one of the highly correlated variables such as x1 or x5. Addressing autocorrelation by moving a time series regression or a Remax model and adding lagged terms such as y sub t minus 1. Reviewing outliers and influential points, either through robust regression or by carefully evaluating and possibility filtering problematic observation. Optionally, a log transformation of the independent variable or some predictor could help stabilize variance and improve interpretability of percentage effect. Overall, the current model already explains a very high proportion of variation in cell, but these refinements would make the structure more reliable, more interpretable, and better suited for real forecasting application.
So far, our next task, performing forecast by applying the box-Jerkins approach, or you can understand as the ARIMA model. First, we have to analyze the characteristic of the given time series data. We will have the achievement distance Fuller test, or we can say the ACF test. We have the null hypothesis is the data not stationary, and the hypothesis 1 is data stationary. We can see that the test value is about 2.81, while the critical value is around 2.86, and the significant level is 0.05, while our p value is 1. So both of these criteria leads to the decision not to reject the null hypothesis. So this means the data is still not stationary. So we have to take the first order differentiation of this data. As we can see at the time series plot, we can still see a clear pattern of trend and seasonality of the given data. You can see that the ACF is actually going down quite slow. After taking the first differentiating of this data, we will do the ACF test again. This time, the test statistic is about minus 3.48, while the p value is 0.008, which means the decision we can reject the null hypothesis, mean the data are now stationary. You can see the final result is written down in the picture. But when we look at the plot of the differentiating data, we can see that the seasonality still happening in this plot. So we are suggested to take another seasonality difference of the data, which means the lag is about 12, as this is the annual data. To continue, after we taking another differentiating, we will do the same thing, is taking the ACF test, which is we can see that the test statistic and p value are can help us reject the null hypothesis, and the data is stationary. But at the end of the plot, we can see that the seasonality is still concluding quite clearly. But based on the ACF and PACF, we are on track on overdo the differentiating, which can lead to an unpleasant result of the data. So we suggest to stop. I think it's to stop the differentiating and start the ARIMA model. For next task, we will identify the ARIMA model using the Minitab. We just choose the turn on Minitab, choosing staff, time series, and forecasting with best ARIMA model. So, and we'll have the final result here. And the chosen ARIMA model with B equal to 2, Q equal to 2 as the AIC, as the statistic, as the numbers for AIC and BIC are the lowest of the given one. To estimate the model parameter, we can have, this is the figure of the parameter. We can see that the coefficient of each parameter of the autocorrelation 1, 2, and the moving average 1, 2, and the constant. We can see that the p-value for these four autocorrelation and moving average is 0. So we can reject the null hypothesis, mean the true coefficient is not likely 0 or not likely 0. But for the p-value of constant is about 0.5, bigger than 0.05. This means we can reject the constant coefficient and it can be removed out of the model. To do the test, we will using the modified box choice of the chi-square statistic. We take the lag of the end of the annual data and the lag 12, 24, 36, and 48. We can see that the p-value are at this value of 0, mean we have to reject the H0 mean the H0, which means all the lags are independent. So the final conclusion we have is the residuals is still containing the significant autocorrelation, which leads to this ARIMA model is unsuitable for forecasting. So therefore, we cannot do proxy the forecasting, generating the forecasting from this model. And that's it for task number 4.
So hello teacher, in task 5 seasonal regression we analyze on YT. So the requirement is perform a regression analysis on YT for seasonal data on chapter 7 and use a model that includes both train and seasonality, and also we need to analyze the results and compare them with the methods that used in test 2 and test 4, which is ARIMA. So what we're going to do right here, so we use regression model to describe the train seasonality in YT. Then we compare, so we use monthly data with period S equal to 12, and we fit the seasonal regression model, which is YT is sales, passengers, or whatever the series measures, and T is bind for time index, which is 1 to n to capture train, and T square is quadratic terms that allow curve trends. DMT is dummy variables for months from 2 to 12, like the month 1, which is January, is the reference. So the YM right here is measures how much month M differ from January, and epsilon T is for error terms. So from this model, we obtain a numerical estimate of train is how fast the series grows, and a seasonal pattern, like which month are systematically above, below January. And also we give a good visual, like actual versus fitted chart, residual plots, bar charts of seasonal effects, and error measure like MAD, MSD, MAPE, so we can compare with test 2 and test 4. So about implementation in Python, firstly we need to read the CSV5 with the pandas and all the data by date, and we import the library in it, and then we create T and T square and month variables to generate seasonal dummies with get dummies, like the command, and to build regressor with metric X like this. And we need to fit an OLS model with stat models like for this comment right here, and we store fitted values and residuals for diagnostics and plots. So we have this charge is actual fitted value. So the blue line right here that shows real data YT over time. The orange line is for value predicted by the seasonal regressions. So it has train and month dummies. So the two lines are very close most of the time, you can see right here. So the regression captures the overall upward trend and yearly seasonal pattern quite well. The fitted line is way smoother than the actual series, so it doesn't follow every spike, especially in 1990s. The model slightly underestimate some local peaks, and in the most recent year, especially after about 2022, the actual series grows faster and higher peaks than the fitted line. So the model under predicts the latest value. So what it tells us? So the deterministic structures like train and flexibility is well captured, but the model can fully follow short terms to shocks and very strong recent growth. In residual distribution, like as you can see right here, we have the histogram of residual. So what I saw right here is the distribution of ET, which is YT minus 4 YT hat, is actual minus fitted, and the safe is roughly bell-shaped, like the center slightly above 0, so errors are reasonably symmetric and not heavily biased. But there are longer tails on the right, so the positive side. So you have several longer positive residual to occasions where the model underestimate the true value, which is actually much higher than fitted. And overall, it's not too bad for normality, but the right tails suggest that some extreme high observations, like unusually strong months that the regression cannot explain well. So residual roughly bell shape. So you can have that. And about the ratio over time. So what is the chart? So the residuals plotted against the time with a horizontal zero line. The residuals are not randomly scattered around 0, and this shows long runs of positive or negative values. And as you can see right here, in early 1990s, mostly small positive residuals, and around 1995 to 2010, a long period where residuals stay negative than positive in blocks. And around 2013 to 2020, many negative residuals appear, so the models systematically over predicts. And after about 2021 to 2022, residuals become large and mostly positive. It's meaning that the model under predicts the strong recent growth. So these patterns means there is strong autocorrelations in the residuals. When one residual is positive, the next few are likely also positive, and similarly for negative. That violates the classical OLS assumption of independent errors and suggests that the data still contain dynamic structures like AR and MA components that is not captured by the train in seasonal dummies. So in ensemble accuracy, like seasonal regression, we have high R square that approximately 0.98. So it's so trained in seasonal dummies explain most of the variation in YT. MAP and MAD are relatively small, so the regression provides a reasonable fit. But however, also correlated residuals, so that part of the time series dynamics is still not captured. So when we compare with the test 2 and test 4, in test 2, host winters and decomposition, host winters gave the smallest forecast errors. And in test 4, ARIMA and SHARIMA models explicitly captures autocorrelation and seasonal dynamics. It means that seasonal regression is less accurate for forecasting, but it is easier to interpret. So regression is best for explaining the trend and seasonal effects, while host winter or ARIMA are better for prediction.